I request I request all the participants to please be muted and only unmute yourself if you have any questions or queries. So let's start. Okay, Lalit, you can start. Thanks.
Okay, thank you. Okay. So, okay, the title of my talk, today's talk is Heavy-quark philic Majorana dark matter, based on the paper as written in the footnote. Okay, in the paper I have other dark matter analysis also, but here I will only talk about the bottom and top philic cases. Okay. So this is the outline. First, I will discuss the dark matter and the effective model. Then I will discuss about my model and then the analysis of that using the relic, indirect and direct detections. And then finally, I will conclude. Okay, so why is a dark matter necessary? So dark matter signals were observed there in various forms. Say, first of all, in 1933 by Zwicky, who observed the coma cluster, and he observed that the mass that he's predicting by the velocity dispersion relations of the galaxies in the cluster and the mass that he's getting from the luminosity by the M by L ratio in astrophysics for a nebula, that is, I think, fixed quantity. So the mass he's getting from both the techniques is not matching. Actually, the mass that he's getting from luminosity is is very less than the mass he's getting from velocity dispersion relations. So yeah, so he said that there is some missing mass inside the cluster. Later on, it was found out that there is a large amount of mass in the intergalactic gases. Okay, but that can only enhance it to about the 10% of the total mass. So okay, so still a large amount of mass is missing. Then in 1970s, Vera Rubin did the same kind of analysis on the galaxies. She studied the spiral galaxies and observed that using the Doppler shift that the velocity of the stars in the galaxy, and also she studied the helium line, okay, to get the velocities of the velocity at different distance from the center of the galaxy, and study that and she got that. Okay, let me write. Okay, what she observed is that the velocity profile for a normal galaxy should be like this. It should decrease with radius. Okay, but it is not decreasing. As she observed that this is going like this. But she said that that is only possible when there is a mass inside the Gaussian surface that she is observing, and that has to be non-visible. Okay, so in 1970s, the scientists also observed the gravitational lensing. So there is some galaxies in the universe, and within the line of sight, there is some the galaxy looks like some kind of distorted in some. Say you have a galaxy like this, and say there is some matter in between that is not visible. Then via this gravitational lensing, this will look like somewhat distorted. Say, so these also observed there. And then the cosmic microwave background, that was the power spectrum of the, okay, sorry. Then there was this cosmic microwave background, that is the radiation from the early universe last scattering surface that happened when the hydrogen became neutral for the first time, and the gamma, the photons, became the universe became transparent for the gamma. Then this radiation background is still available. Temperature of this radiation background is around 2.73 Kelvin. Now, this has been observed in 1990s, 1989, I guess, by the Cove explorer, and it says that the spectrum is almost like a black body, and there are slight anisotropies. Now, if you plot this whole spectrum in terms of the correlation function and generate the power spectrum of this, we get some spectrum, and I don't know how they study it, but they said that they can predict the baryon content as well as the total matter content. And when they observe it, the matter content comes out to be, say, this is mh square. Omega is the ratio of matter, density of matter times the critical density of the inverse. So this comes out to be this 133 something. Okay. And for the baryonic matter, that the visual matter that you observe, that comes out to be 0.02 something. Okay. So this clearly you can clearly see here that there is a large amount of matter that is not visible to us, that is not coming out from this observation also. Then the Big Bang nucleosynthesis, it says that in the early universe there is this hydrogen annihilating to give me, sorry, fusing to give me the deuterium. Now deuterium is also created in the stars, but in the stars that deuterium is again getting some more after some reaction that instantly gets converted into the helium. So the deuterium that is available in the universe is mostly dominantly by coming from the early universe Big Bang nucleosynthesis. So this D by H ratio, the amount of deuterium by the amount of helium in the universe, is heavily related to the uh, amount of this matter, this one. Okay. So this also says that the this one, the baryon content. So this also says that the matter I'm getting, the visible matter that I'm seeing today, the standard model part, that is very smaller than the total matter content of the universe. Okay. Now there is a recent signal also, the blood cluster in, I think, 2006. It says that if there is two galaxies that are going to collide each other, and it's like, say, you have two galaxies, they are coming close to together, and they have also the dark matter around them. Okay. Now when they pass each other, this visual matter, this via some other interactions other than the gravity, this velocity after the collision, it slows down. But for this dark matter, they passes because there is no interaction between the dark matter and the standard model. So they, okay, maybe there is interaction, but that is not as large as the interaction that we have in the standard model. So this pass. So when we see the, again using the gravitational lensing, say, okay, so if there is some galaxy behind it and we observe, say, here, and we are here, so during the line of sight, you will see that this is this line, uh, the light that is coming towards us, why this is getting distorted, but also there is this part also. So a large amount of distortion is happening from this area where you are not seeing anything. And okay, so this is also observed, and it also says that the dark matter interaction is also very small. Okay. And finally, the structure formation, it says that the amount of matter that we require for structures to form at the current time of the universe is not enough from the visible sector. You need extra amount of matter that is not there. So it has to be some dark matter. Okay. Now why effective interactions? So as we know, the standard model has been able to explore all the experimental data that we are seeing, and it can easily explain most of them, but still there are some that are not being explained. Say the low energy things, that the RD, RK, and okay, and this G-2 norm. So people try to extend the standard model in order to explain these discrepancies also. So now the colliders have already explored this to a large mass range, so large energy range. Okay, so if we are doing this, observing some other observable, say this B physics and all, so these are low energy observables. So we don't need to stick to the whole current model, the UV complete model. So for that, it is unnecessary to work with the whole spectrum of particles and just work with the necessary degree of freedom at the low energy scale. So you can integrate out the higher degrees of freedom. Okay. So it says that also it is a point that majority of these models at low energy, they give the similar kind of structure, similar kind of physics. So it is easy to work with the effective interaction at the leading order. So okay. Okay, using so now since dark matter interaction that I am considering in this model are relic direct and indirect detection. Both are low energy compared to the collider energy range. So I will only consider the effective interactions here. Okay, so I am okay in this model. I will take the real dark matter, the Majorana dark matter. Okay, so for Majorana dark matter, there is scalar interactions possible. There is pseudoscalar, but there is no vector and there is no tensor interactions. This kind of interaction and this kind of interactions are not possible because of the self conjugacy of the chi particle. Chi is my dark matter particle. Okay. No. So these are the possible interactions that I've written for the scalar, pseudoscalar, axial vector. And there is one more, the twist operator. So okay, the motivation for these operators is like we could have a higher energy, high scale model where the interaction is mediated by scalar, a pseudoscalar, axial vector, or as well as a heavy graviton. Okay, so this twist operator, these structures, okay, these are not exactly the interactions that are in the graviton. Okay, so if I clearly say that the graviton interacts by using this eta mu nu, then t mu nu. Okay, here I am taking the tensor twist operator, which is just the t mu nu minus half of the trace of this part. Okay, so this trace is almost equal to the scalar part with at the dimension 8 operator. So it will not be that much contributing to the case. So it is approximately the
Hello, Lalit.
uh,
I have a question. So, in each EFT operators, you have two chi's. What is underlying symmetry? Like, is it because of Chateau symmetry? Or means there is always two chi's in your EFT operators. Is it possible to write two interaction for one chi, three chi, or any odd number of chi's?
No. Actually, okay, I am taking this Z2 symmetry. So if this is odd, I cannot write an operator that has this odd number of chi's.
So why do we need this?
Otherwise the dark matter will decay. I'm not considering the decay case.
Okay.
Okay, the one reason for being the dark matter to be stable is that okay, I am taking a dark matter at the early universe, and I am also seeing the dark matter at current time. So I will assume that the dark matter there and now it has not decayed too much, or it like almost have not decayed. So I'm reducing that possibility by taking it stable. Okay. Okay, so that so here I have this one, the twist operator that is related to the heavy graviton model. Okay, so these are the four operators that will occur in this case. Okay, now this twist operator has been defined like this. Okay. And the Q here represents only the top and bottom. Now, okay. Now dark matter in the early universe was in the in this case I am only talking about the WIMP dark matter, the weakly interacting dark matter. Okay, at the weak scale. So this kind of dark matter, it was in a thermal equilibrium with the standard model particles. So it means that the chi to q bar process was going from one direction to the other and reverse direction with that this direction was in equilibrium. Okay, as well as this chi q to chi q and q bar also. Okay, so in order to maintain the chemical as well as the thermal equilibrium. Okay, now as the as time evolves, the universe expanded, and with the expansion, the temperature of the universe also decreased. Now, as the temperature is decreasing and it is expanding, two things are happening. The kinetic energy of the dark matter is reducing, and the phase space, the possible number of dark matter that is available for the other dark matter to collide, for this reaction to happen. Okay, this is decreasing. Okay, so this, so the forward to backward, sorry, so this side reaction is will get okay, after some time this kind of reaction will stop, this direction stop. Okay, so only this will happen after some time when this condition satisfied. And this is also written like that the annihilation rate gets smaller than the expansion rate, where annihilation rate is n chi times sigma v. Okay. Okay. So when this happens, the the formation of dark matter particles stops, and only dark matter annihilation annihilation to QQ bar remains. This process remains. Okay. After some time, when the universe of further expand, this annihilation also stops, and the number density of the dark matter remains constant. Then that means the freeze out. Now, by constant, I mean that the co-moving density, co-moving number density of the dark matter is constant, not the total density, as the universe is evolving. So, with time, only co-moving density, the total density is okay evolving with this a scale factor. Okay, now, so now if we have this cross section, this one, in the form of this a plus b v square, as I can expand my this the s by 4m chi square plus, and then plus 3 by 4. Okay, so this s is my this invariant mass of my two dark matter particles. So I can, as I can expand and they get my cross section, this one, the thermally average cross section in terms of a plus b v square, then I can get my relic density using this formula. This formula is derived from the Boltzmann equation. Okay. Now, where this
Hi,
G
hello.
is
Hi, Lalit. Why there is no linear term in B?
linear term in B. Okay. Oh, okay, because this is a scalar quantity. Okay, and if I write a linear term, it will be like this. Okay, even I can also see that this is a Lorentz-Zingran quantity, so you cannot even write this type of term. It has to be invariant. So v square is
Okay, thanks.
okay. So this G star F is the number of degrees of freedom at the time of freeze out temperature Tf. Okay, like this temperature is at the temperature at which the this reaction stopped happening from chi to QQ bar. Okay, and the number density is constant. Okay, and XF is defined like this: mass of dark matter by Tf. And yeah, now using this value, which is 0.1198 from the Planck that recently gave in 2018, I will try to constrain this sigma v. Okay. Okay. So using this constraint, I am fixing my dark matter mass with the coupling, not coupling, but this factor. This is approximately lambda, you can say, for c is equal to 1 case. Okay. So this is the shaded region is the allowed region. Says because my relic density has to be this or smaller than this value. Okay. So the smaller than this value will give me the upper bound on the sigma v, and hence on, yeah. Sorry, let me say it again. Okay. Constraint in say that this is more than 0.1198. Okay. So if I'm taking it smaller than some value, then this value has to be greater than some value, and this means the c by lambda square has to be greater than some value, and then inverse that lambda has to be smaller than some value. So this is giving me a upper limit on the lambda. Okay. So for all the 4 operators, I have derived this upper limit. Okay. Now using these allowed values of the c by lambda square, or say lambda, I will try to constrain the indirect and direct detection cross sections. Okay. Now indirect detection. Now in the as I said that in the early universe, the relic density of the dark matter is constant. So it is, so now today this dark matter density can be very much in this dark matter can be found in very large amount in the gravitational potentials, because dark matter is interacting via gravity. Okay, so centers like a galactic center, the dwarf spheroidal galaxies, or the center of the clusters, okay, there the possibility of dark matter interacting with each other can increase, because the density increases from the average density of the universe by around a factor of 5 or 6. Okay, so in that scenario, when the dark matter annihilate and the reaction this reaction happens, the chi to ff bar, this ff bar, this standard model for particles, in my case the bb bar and tt bar, can be observed, but we cannot observe the bottom and top. So this will hadronize, and I will only see the hadronized some uh, other products. Okay, so if this is happening, so in this case, say I have a tt bar production. Now t goes to bw with a branching ratio of around 100%. Okay, so in both cases, bb bar bounds easily cross section for this. Now for B, and so how will this BB bar, how will I observe this BB bar? So I have a bottom that will hadronize, and that hadronizing will give me some pions. Now pi naught gives goes to this channel by around 90% of branching ratio. Okay, so I can observe these photons with this experiments do. They observe the photons, and from this photons they back plot to the same phone and tries to extract the cross section for this chi to ff bar. Okay, so this cross section has been provided by this FermiLAT and H.E.S.S. Okay, here I have calculated the theoretical cross section from the operators that I'm using, and as you can see, the cross sections for the scalar operator is velocity dependent at the leading order, and for others it is a not. Okay. Now, so okay, one more thing, that okay, this C is the number of color for the top and bottom. This psi f is defined as square by m chi square, and v chi is the relative velocity of the two dark matter particles. Now, one more thing, that in the universe, the dark matter was present at very high temperature. So the relative velocity was also very large. Okay, now okay, in early universe, I can say for the relic case, it was around 10 to minus 1 of the speed of light. But in say the center of our galaxy, okay, it is around 10 to minus 3 C, and for the dwarf spheroidal galaxies that I'm using is for 10 to minus 5 C. Okay, okay, and I'm using for dwarf spheroidal galaxies. Okay, I said. Okay, these are satellite galaxies. Okay, in the halos of say our Milky Way also there are some galaxies, and if we observe them, then they have a low amount of visible content. So because of that, the spectrum, the photon spectrum that is coming to us is not that much affected by the background. Okay, we can say that the signal coming to us is not like the galactic center signal, where there are large number of other, say, stars and neutron stars, and a large amount of intergalactic gas also. So where the signal can be distorted. So the signal coming from this dwarf spiral galaxies is a good, okay, good quality. Okay. Okay.
Hello,
So now
Lalit.
from this value, yeah.
I just have a question. The nature of your, since you are considering your dark matters as spinors, right? They are quarks, right? So are they the fields? The fields are invariant, and are they singlet under the standard model symmetries, or they can transform?
No, the dark matter particles are singlet.
They are singlet,
They,
and then
they,
okay,
they cannot have any electromagnetic or any strong charge, because if they had, we could have easily observed them easily in the LSC, because LSC can produce large amount of this quark and gluons can directly hit them.
Okay, that's why you're considering they have mediators, and then
yeah, even in the BBN also gives bound on these things in the strong and the electromagnetic sector, because BBN has this nucleon interactions. So if some particle is there, then it could have changed something there.
Okay, thank you.
Okay. So if you see for this case, this velocity is very suppressed. So this cross section will be very suppressed. Okay. So so since this is around 10⁻⁻10 or suppressed, so I will not show that, and I will only consider the other three cases here. Okay. So you see the two cross section, the pseudoscalar and the twist, are around 10⁻26. That is the same range that is allowed by the relic density calculations, as I have given there. Okay, I have not in this there, but this is same thing. There is no suppression. This Wilson coefficient from the allowed region of relic density will give me the same cross section for the indirect detection. For axial vector, you see that there is one interesting thing happening, that the curve is decreasing. So what is interesting happening here is that this term, which is not there in others, okay, so this is mf square by m chi square. So now for low values of dark matter, this term, if I write it, it is 1/3, 1 plus 1/3, and then m chi square by mf square. Okay, for low value of dark matter, say around the mass of the Fermi on the bottom or top, so this is of the order of 1. Okay, so from a relic case, since the velocity is very large, okay, both terms will contribute and gives me a bound on the coupling, or the lambda, say, on the Wilson coefficient, if I say simply. Okay, now that constraint, when I'm doing with this case, indirect detection, in this case, even if the mass is very large or very small, it's not going to change. Okay, now further, if I go to the large dark matter case, this value will increase as compared to these, and this will dominate. As I said, this is very 0.1 square in case of relic. So this will give me mostly the bound on the Wilson coefficient from the relic, but in case of indirect detection, this will not, because this term is already suppressed. So because of that because of this factor, this curve is going down for large masses of dark matter, okay, on both the cases. Okay. So the colored region is disallowed from the relic density bounds, and the region above this H.E.S.S and this FermiLAT is also disallowed. So only the region between these two upper and lower curves is allowed. Okay. Now for the direct detection. Now in our case, since we have only the bottom and the top degrees of freedom, and these degrees of freedom are not present at the nucleon level. So what possibly can happen is that these two particles will be present only in the loops, and what interacts with the nucleon is the gluon. Say via this channel, I have this chi, and then I have the top loop, and then the gluons. Okay, now these gluons will interact with the nucleus. They will be present inside the nucleon. So this is a possible channel that can happen. Okay. So first of all, what I will do is I will convert this part into this part, and that will give me this kind of operator times this, which is this is a loop factor, and this is here for the scalar and here for the axial vector. Now for pseudoscalar, I haven't shown it because for pseudoscalar, the interaction will come out to be g mu tilde, and this is a spin dependent, and I will come to it later that it will be suppressed. Okay. For twist, the leading order, there is a divergent term coming. So I will use cutoff regularization. So from this, the lambda is the cutoff, which is the scale of minor physics also. So this factor will come for the loop part. Okay, and the structure is same as the gluonic tensor, gluonic twist tensor. Okay, so now using this dark matter gluon effective interaction, I can see what is the cross section for the dark matter with the nucleon. Now I am going from top to the gluon degree of freedom by solving the loop, then from gluon, which is partonic degree of freedom, to the nucleon degree of freedom. Okay, so for that, yeah, so for that I have to match the nucleon matrix elements. Now for as scalar operator, this one m q bar q or the g mu nu, both are scalar operators. They are related to the energy-momentum tensor. Okay, and these are scalars, so it will be the trace of this. Okay, now okay, and the trace is the energy-momentum tensor for the nucleon states. I can easily extract. So from that information, the trace, which will give me the from here I can relate this n bar n state, which is the nucleonic state, to these two operators. Okay, so using these operators, I get that what is the so the nucleon matrix element will give me what is the probability of the contribution. What is the relative contribution of the quark, and what is the relative contribution of the gluons inside in the mass of the nucleon, total nucleon. Okay, so this is given by these factors. Okay, okay, I have given it here. So, okay, this is the exact formula for that. So the OG is this factor. This is OG. Okay, so this will give me FTGN. So now if I calculate the cross section, I will have these for the scalar. Now for the pseudoscalar, similar kind of nucleon matrix element will be there, but this time it will not be related by the mass of the nucleon, but by the spin content of the nucleon. Okay, so that will give me this, and yeah, you can say here this Sn is the spin of the nucleon. Okay. Now in case of twist, as I said, this is a tensor, and this tensor related to the energy momentum tensor. So this time I don't need to do the trace of the stream, and from okay, this T mu, the energy momentum tensor, is related to the parton distribution function of the nucleon that we have studied. These are the same distribution function that we have studied in the protons, where in the LHC that we convolute with the probability of quark and gluon that is coming from them. Okay. So I have this is the second moment of the parton distribution function. Okay, so at the cross section level it will be square. Now these are the cross section, and as you can see, I have also taken the order of estimate of all the cross section. As you can see, this is 10 to the minus 46, this is for 57 and 58. So first I will come to the spin dependent case. As I said, for the pseudoscalar case also, this kind of structure will happen. And also for axial vector also, this is the structure. So for both the cases, the cross section will be spin suppressed. Now in this case, as you see, this is 10⁻⁷. The experiment found in this cases are 10⁻42 or 43. So it is, these operators cannot be constrained from this direct detection scenario. There is a large amount of it is almost allowed from these direct detection experiments. What we can constrain is the scalar and the twist interactions. Okay, so for an experiment, it is around 10⁻⁻47 the centimeter square, the cross section value. And yeah, okay, from here, so from the xenon 1T and panda, these are these lines. Sorry, I have constraint, and these are the for the bottom philic scalar operator for bottom philic top cases. As you can see, the top philic is almost allowed for whole the range, but the bottom philic is not allowed. This is excluded for almost all of the range except at the very ending of that. For the top case also, this twist operator is allowed, but also for this scalar operator also it is allowed. This is because in the operator, as you have seen, yeah, in this operator that you see, there is a mass factor here, and because I have tried to keep my operators in a gauge invariant form. So I cannot write QQ bar directly because QQ bar is not gauge invariant. So so MQQ bar is gauge invariant because this phi can give mass to the quarks. Okay, so by writing this in the gauge invariant form, I have a MQ factor here, and this MQ factor is for this case is not helping any for this parameter space, but for this case, because the top quark mass is very large, so a large amount of parameter space is still allowed for the top philic case. Okay. Yeah. So finally, I will try to see, so for both the scalar and twist operators, what are the prospects in the future that I can constrain for these two operators. So here I have given the differential nuclear recoil event rate. So this is okay. This is related to the okay. This the interactions can happen with the nucleus of the detecting element. Okay, so in our case, in the experiment that just mentioned, this is a xenon 1T. So as the name suggests, this is a xenon nucleus that is around 132 atomic mass. Okay, now a dark matter particle can hit that particle, and I can have a recoil of that xenon particle that can be observed. Now how the dark matter how the recoil will be observed is one thing, and how the dark matter is available around our nucleus, yeah, our target, is another thing. This is one is the astrophysical part, and one is the particle physics part. Okay, so all the particle physics content is here in these things. Okay, and the density. Okay, and the cross section, and then the particle physics part, that how it can interact with the nucleus, this is given by the cross section. Okay, so rho is the okay. So this rho is the density of the dark matter around us, and that we can easily extract from the observations of our solar system or our local group in the Milky Way. So this can be calculated. Okay, now the another thing is this FV, the distribution of dark matter. Normally people take this to be Maxwellian distribution. Okay, which fits with the spherical halo distribution model that has been established, I think, around 1970s, and has been quite successful time. Okay. And finally, this is the dark matter nucleus interaction cross section rate with respect to the nuclear coil energy. Okay, now here, now this cross section can be further converted for the spin independent case into sigma n a square, and this mu n square. I think there is some m nucleus here and v square here. I maybe some factor here. Yeah, this f here. Okay, here what is happening is the for spin independent case, since the interaction is not dependent on the spin, and I am also assuming that the interaction of the dark matter with the neutron and the proton is same, so I can easily say that the interaction is happening with one of the nucleon times all the number of is constituents. So yeah, so I can easily convert this section to this in the limit of zero momentum transfer. Okay, zero momentum transfer, I'm saying that that the experiment is not, oh sorry, the dark matter is not able to explore beyond the neutron or proton, the nucleon. Okay, so this information gives me, simplifies my cross section in this form, and f q square is the form factor, that is for a nucleus what is the distribution of the constituents inside that, or the inside that. So now using that, I can convert it into this form. If I integrate my coil rate with the energy range that is available to me from the threshold energy, it is around 2 or 3 kV, to the maximum energy that the maximum recoil energy that the experiment is sensitive to, I can get the expected number of recoil events. Okay, so now sigma n is available to me, that I've calculated for the direct detection. Okay, other things are also available to me. The thing that is not available to me, this exposure. Okay, so what is this exposure? Exposure is that the amount of target, say the amount of xenon is available to me, and for how much amount of time it is there. So this is the exposure. So this is kind of the flux that the dark matter over the time will see to interact. Okay, so now, so since our experiments have not been able to find any event by now, so this thing can be used to constrain the sigma n, the parameters of the sigma n, that is the coupling, the Wilson coefficient, and the mass of the dark matter. If I plot it, yeah, here. So if for all the 4 spin independent case, this button, as I said, this is already ruled out to 1.8 of dark matter mass now, and for others a large amount of parameter space is available. So in future, when say the exposure, so by exposure the quantity of the xenon will increase, this will almost be ruled out. Okay, and the others, as you can see, this magnitude that is to be, the exposure that is to be needed to exclude these other operators is very large. So if I increase the exposure from 1 ton year to 10 ton year, that is not enough. I need several years with a large amount of xenon to exclude this operator. Okay, so these cannot be excluded by these. So these are still allowed for a long time. Okay, yeah, is it? So now finally, I have constrained this from the relic and the direct detection spin dependent scenarios only simultaneously. So the upper limit is from the relic case, okay, this line, and this lower line is from the direct detection. So the reason between them is allowed from both the experiments. Okay, and please pardon me because I have green so gluon case also, which I could not remove. Okay, now you see again this one bottom is disallowed, and also the coefficient is very large. Okay, others we have a very others, for other scenario I have a quite a good amount of parameter space that is remaining, that has to be explored in this scenario, in the detection scenarios also, like correct. Okay, so finally I will conclude. I would say that we have constrained or the allowed thermostats for the Majorana dark matter that is interacting with the bottom and top using this scalar, pseudo-scalar, axial vector and twist operators. And from the relic density, direct detection and indirect detection experimental bounds. Okay, and we conclude that the bottom philic case for the Majorana dark matter scenario for the scalar interaction is almost excluded. Okay, thank you.
Thanks, Lalit, for this wonderful talk. And the floor is open for questions. If anyone has any question, he can mute himself or herself and ask.
So Lalit, maybe you can give us some references on archive, for audience who are interested in going further.
Okay, for dark matter. Okay. Okay, by calculation wise, if dark matter we are studying, we have to also follow the cosmology part also, and I think that is followed from Tillman, some a review lecture by Tillman Plain, and I also follow this lecture by Lisanti. She also gives a nice uh, discussion on how other also available. Let us say for from various things you can say that dark matter cannot be the mass of dark matter cannot be very small. Okay, and also explains the difference between the decoupling and the freeze out there. This is a good lecture by her. She also if you want to follow this uh, uh, this early inverse scenario, then I think Dodelson that I followed is good. It's a book. Yeah. See, I cannot give more references that are not coming to my mind, and I'm sitting some other's lab, so I don't have my laptop right now.
Okay.
I can email later.
Yeah. Thank you.
Lalit, I have a question on slide number 5. Like you mentioned that you are only considering the third generation quark for in your model for the coupling to the dark matter. Is there any reason for that? Like the coupling with the dark matter of these quarks are like why you are considering only third generation quark?
Okay. There is no specific reason, but you can say for a light dark matter that a large thing has been either ruled out or highly constrained. Say from say collider, you have the light quarks. The amount of light quark that is available in the PDF, pardon distribution functions, that can easily interact with at the tree level to the dark matter. Okay, say you have some UDS that is already available in the proton at large quantity. So if you have a PP collision, okay, then the possibility of this kind of process, okay, kind of process is large. Okay, so these are already constrained, and also and also this scenario also can easily constrain from the direct detection cases, because in direct detection I don't need to solve for the loop. So now there is not loop separation for the interaction. So this will be highly constrained from that scenarios.
Okay. Okay, thanks. Okay, if there are no further questions, then we can thank the speaker for this wonderful talk.
Thank you.
So I think Navdeep, we can stop the recording.